All right, so this is one of the harder problems we've encountered. So let's just kind of work through it. What's going on is you have a track. It's horizontal, so there's no potential energy due to gravity involved. A block is placed here at 0, and it's in contact with the spring. And then it is pushed back to this position here, so the spring is compressed, and then it's let go. So the block is going to gain energy from the spring, and when it gets here, the spring is no longer compressed. And so it's going to have all the energy of the spring, and then it's going to slide along a rough surface until it eventually comes to a stop. Okay? And we have to figure out what's going on in this case. So the first thing they want us to do is sketch on the graph the following two quantities, the kinetic energy and the potential energy of the block spring system. I'm going to start with the potential energy because there's no gravity involved. It's not moving up or down, so no energy is being stored as gravitational potential. So the only energy that is stored in the compressed spring. So when the spring is not compressed, there is no potential energy stored in the system. So right here, I know that my potential energy must be 0. Okay? There is no energy. So when it's pulled all the way back to here, I start off with some energy. I'm going to say it's right there. Doesn't really matter, the scale. So the question is, what happens between here and here? Well, remember the potential energy in a spring equals 1/2 k times the distance it is compressed squared. So as we compress it more and more, the energy is not linear. This is not a straight line. It's actually a parabola. And so what we're looking for is to see if you understand that it somehow goes in a nonlinear fashion down like this. Okay? So the potential energy is all the energy is in the spring, and there's no kinetic energy. And then when we get to the equilibrium point, back to this point right here, no energy is stored in the spring, so all the energy is kinetic. And so if this decreases quadratically, the total energy's got to stay the same. This has got to increase quadratically, so it's going to have to somehow, the kinetic energy is going to have to rise something like this. Okay? All right, for the rest of the time, there is no energy stored in the spring, so this is going to be 0. And the next thing that's happening is energy is being lost as it slides along the rough surface. And so remember, the work that is done by friction is the force times the distance. The force of friction is going to be the same. It's going to be mu times m times g. Sorry, you can't see that. Times the distance that it has slid. So when it slides twice as far, it loses twice as much energy, so that's a linear relationship. And so we know that the energy is going to decrease linearly, the kinetic energy. Okay? Now, if that's all you did, you are correct, but you're not going to get all your points because it says to sketch the quantities and label them. So we just need to label them. This here is the kinetic energy of this system, and this one down here is the potential energy, which you can call PE or you can call it U. Doesn't matter. The answer key calls it U, but that's what our graph looks like, and that's a fairly difficult problem to figure out. Okay, and I think all of that got you 4 points. Yeah, so realizing the kinetic energy increased and then decreased, got you a point. Realizing the potential energy decreased and then was 0, got you a point. Realizing that this was not a straight line, it didn't decrease linearly, got you a point. And realizing that this was the mirror of that, got you a point. So there were 4 points there. Okay? All right, so now we have to talk about what's going on. The spring is compressed twice as much. A student is asked to predict whether the final position of the block will be twice as far. That's 6D. The student reasons that since the spring will be compressed twice as much, the block will have more energy when it leaves the spring, so it will slide farther along the track before stopping at 6D. So you are asked which of these aspects are correct and which are not correct. So the student is correct in noting that compressing a spring more will store more energy. And if it stores more energy, the block will have more energy. It'll slide farther. So that's correct. The student is incorrect, though, in saying that it will go a distance of 6D. Okay? So that's the incorrect part. since we double the compression, it'll quadruple the energy, and if the energy is 4 times as big, it'll go more than twice as far. Okay? Now, here's where the real money comes in. You have to use quantitative reasoning, numbers, equations, to develop an expression for the new final position of the block. All right? So I did that right here. Originally, the energy of the spring becomes the work that's done. So 1/2 kd squared, that's the energy in the spring. That's going to equal the force times the distance the block slides. So the force is friction, mu mg, and the distance is 3d. Now, for the second launch, same thing. The energy of the spring must equal the work that's done on the block. The energy in the spring is 1/2 k times 2d squared, and that's got to equal mu mg times x, the new distance it goes. I can pull out this 2 squared and write a 4, and then I can write 4 times 1/2 kd squared. I know 1/2 kd squared is mu mg times 3d, so I can put that in here. So I have 4 times mu mg 3d, and that's got to equal mu mg times x. So I basically substituted in equation 1 into here. And then the mu mg's all cancel there, and you're left with 4 times 3, or 12d, equals x. So you have derived an expression for the distance the block slides, and it is 12d. All right? You can also reason that qualitatively, but it said quantitative, so this is not enough. You have to show it with equations. Since the energy stored is proportional to delta x squared, compressing the spring twice as much results in 4 times as much energy. And since the distance it slides is proportional to the energy, having 4 times as much energy will mean it'll slide 4 times as far. So instead of going 3D, it'll go 12D. All right? Now, this last one I think is a bit goofy. I feel like you could really understand exactly what was going on and even get this answer and still not be quite sure what the heck they want you to do here. They just want you to explain how the correct aspects of the student's reasoning from part B are expressed by these relationships. So right here, the energy stored in the spring equals the work. The energy stored in the spring is 1/2 kd squared. So saying that if d gets bigger, the energy stored in the spring is bigger is using this relationship. So we can say the student is correct. The energy in the spring, 1/2 kd squared, means that increasing d will increase the energy stored in the spring. That's an argument the student made, and that's correct. The incorrect thing is supported by our result here. The distance it slides is 12d, and so the student's claim that it slides 6d is incorrect. So from the result x equals 12d, we can see the final stopping position is not 6d, but rather 12d. So that's how our equations show the incorrect reasoning of the student. Part D, everybody who I've ever talked to thinks it's a really goofy, kind of weird question that we're not quite sure makes a whole lot of sense, but they're basically trying to just ask you to go back and compare your equations here with your reasoning up here and see, do the equations you have support the reasoning you gave up in B? So that's a pretty hard question, but it's a fairly common one. And if you had to ask me, what's my bet on what is the one, there's only 2 questions on this AP exam, what is most likely going to be on it, I would think something having to do with energy is probably a good guess. So that's why it's important to kind of understand this. All right.